Okay, so I think we're live now. We're just waiting a few minutes just to let people filter in, but I think most people seem to have arrived now. So I guess we can get started. Okay, so welcome everyone, and thank you for joining us. My name is Dr. Anthony Kiley, and I'm a postdoctoral research fellow jointly at UCD School of Physics and Sequest, which is the new Center for Quantum Technologies at UCD. And I'll be hosting the talk given this evening by Professor Klaus Mølmer. Just before I start, I just want to say a big thank you to everyone who helped me in the organization of this, the National University of Ireland for awarding me the grant to run events like this, Science Foundation Ireland for funding my current research position, and all the help from various people at UCD and Sequest, specifically Professor Steve Campbell, who was loads of help and is also with us here tonight. What is the topic of this evening? What is it all about? What's the motivation behind it? Well, at least personally, I've noticed a lot more media interest recently in quantum technologies. It seems like there's a real uptick in this. And this is often centered around this push for a quantum computer by big tech companies like Google and Microsoft and Intel. So I feel it's definitely something which is becoming part of the public radar, like in the back of your mind. Maybe you've heard a little bit about it, but don't have a coherent kind of clean idea of what is this all about. So the hope tonight is that by the end of this evening, at the end of the presentation, this whole idea of quantum physics and quantum technologies will be, just a little bit clearer. On that note, I should say, if you do have a question during the talk or you don't understand something and you say, what's that? At any point, you can write in the Q&A feature anything you want me to ask. And then at the end of the presentation, I can direct your question to Klaus and he can answer it. I suppose the other big motivation for organizing this is quantum physics and quantum technologies is also becoming a big topic in Ireland. So there was recently the launch of this Sequest Center at UCD. There's also a new quantum center at the Tyndall National Institute in Cork. This year, Trinity in Dublin are launching a master's program specifically in quantum science and technology. So Ireland is really starting to become kind of more of a hub for this kind of research. So those would be kind of the kind of secondary motivation for kind of explaining this, seeing as this is becoming more part of the Ireland research scene. So with all this in mind, we're going to hear from Professor Klaus Mølmer, who's really a leading figure in theoretical quantum optics. He's currently based in Aarhus University in Denmark. He's worked with many famous physicists like Peter Zoller, Alan Aspect, Claude Cohen-Tanucci. He's pioneered things like the Monte Carlo wave function, description of dissipation, and the kind of now famous Mølmer-Sorensen gate. And clearly he has a keen interest in public outreach. He's given many public lectures in multiple languages. So we're really very lucky to have him here with us tonight. I could keep going on and on about hundreds of papers, many awards. I think I'll probably stop here and I'll just say that I'm really looking forward to your talk this evening, Klaus. So with that, I think I can stop sharing my slide, and Klaus, whenever you're ready, you can share your slide and take it away.
Good. So thank you very much. I'm just trying to see if I can. I think you as a host, you have to open my window, at least if you want to see my face during my talk. But my slide I can definitely share. So here we go. So thank you very much for the very warm introduction. On this very first slide, I would like to tell you what kind of talk I'm going to give tonight. This is a picture from Aarhus University, our main auditorium, where I'm giving a talk, which is a public lecture, the same style as this one. We are giving in Aarhus 6 days per week, at least 10 different popular talks every day. So we have crowds of people coming every night to the university to hear talks on any topic. So we have really managed to cultivate this idea of public lectures. This particular lecture series in which I'm speaking here, we had an audience of about 2,500 attending each talk. And then we realized that's not going to work. We cannot fit into the building, and it's a pity for all the people who cannot be here. So we started live streaming, not to individuals, but actually live streaming to movie theaters and to schools and churches and whoever would actually like to get the feed so that they could see these talks. Never individuals, actually. We always insisted that it had to be a public showing. There should be coffee in the break. There should be somebody saying welcome, because we also found out that it was maybe not, at the end of the day, not so much the talk. It was actually the good company of other people that attracted people to the talks. So they come and they have a lot of chat before we start talking about this physics or whale catching or whatever is the topic of the night. And we could almost not kick them out of the room again because people wanted to continue their discussions about everything. So in this picture here, maybe I can actually find a little tool so I can show you what I'm pointing at. So there's a little spotlight here. So on all these little dots are public showings of these public lectures, apart from the live audience, of course. And up in this small village here, which is a small fishing village, we have actually a good tradition that the fishing boats are pulled onto the shore in the evening. And in that little village, most of the people also came to hear this talk. So here you see a lot of fishermen and their relatives sitting, listening to a talk about quantum computers. I'm not sure that helped them a lot in catching more fish the next day, but I'm sure the coffee and maybe a beer and some alcohol after the talk made them better friends with their neighbors and gave them a good day on the sea the next day. So the talk I will give tonight is actually an English version of such a popular talk. So for the physicists in the audience, well, maybe you could get inspiration how to explain the quantum physics to your friends and neighbors. And to the non-physicists, I hope I'll be able to give you a little flavor of what is this crazy quantum mechanics. So the title is Quantum Physics and Quantum Technologies. And then I put here the subtitle from weird, because quantum mechanics is a really strange or weird theory, to wired, because in the last few years, we are actually trying to wire up things and do things that work by the principles of quantum physics, which are really strange. We are not so much using the quantitative properties of atoms and matter as we are using the craziness of our description of that matter. You may know that leading actors in physics, Albert Einstein, who you see here on the left on his bicycle, and Niels Bohr, who you see here on the right on his motorbike, that those two gentlemen were for their whole life disagreeing on what quantum mechanics means. And the fact that brilliant physicists who are co-inventors of this theory actually for half a century keep discussing what this theory is about and never agrees upon what this theory is about shows you there's something fishy or indeed very weird in the theory. And I try to show that to you. It is not something mysterious, except it is very strange. So let's get going. I will tell you about quantum physics. The first part of the talk, the amazing and very strange quantum mechanics. It works. It's a fantastic theory. Natural scientists never produced a more precise theory of everything as the theory we have made for atoms and the atomic world. And then I will go to the quantum technologies. And in fact, I will put my focus on the quantum computer that Anthony was also talking about. I'll tell you how they work, what they do, and how we are now building them actually, not only in the laboratories, we also have now industries, big industries that are building machines that can work as quantum computers. So this is the from weird to wired part of this presentation. So let me take you back to the beginning of the 20th century, actually the end of the 19th century. Physicists understood a lot of the world. We understood classical mechanics since Isaac Newton. And in the 19th century, we also started understanding electromagnetism, the theory of radio waves, and also electric phenomena through the work of Maxwell. There's a phenomenon that people did not understand, but hoped they would find an explanation of. And that is illustrated by this picture of a fireplace. So you know, a fireplace looked like this. You will probably also know that the red glowing part of the fire is not as hot as the yellow glowing part, which is not as hot as the white glowing part of the fireplace. Now, color is something we know how to describe in numbers, in physical terms, And temperature is also something we know to describe. But at the end of the 19th century, nobody had an explanation of why hot means white and colder goes to the red colors. There was just no formula, and there was no understanding of why that happened. Our understanding of light was that it is electric and magnetic waves. Light has characteristic frequencies at which it oscillates, and Maxwell is very famous for that theory. The red colors oscillate more slowly than when you move into the yellow and towards the blue colors of light, or the colors you see in the rainbow and the sky, for example. But there was no explanation of why hot and cold should be related to that. The explanation came the year 1900 by the German scientist Max Planck, and he said, we have to understand, of course, this connection between frequencies and color, but inside these wave phenomena, there is a kind of particle phenomenon. There's a kind of quanta, which is the smallest packet of energy you can have in radiation. And he made this postulate or claim that the energy associated with the temperature in the fireplace is actually because light is emitted in these quanta. And he postulated the formula that I put here, that the energy is a constant. We call it Planck's constant. He was, of course, modest enough not to call it Planck's constant, but the constant times the frequency of light. So it's not only a matter of the intensity going up and down when you change the temperature of your fireplace. It's actually also the frequency which is going up and down. But since frequency and energy is the same, and energy and temperature is also the same, there is actually a connection here between the frequency and the colors of the light, so to speak, and the temperature. Planck was not only writing this formula, he was writing a very famous formula that I don't want to show you here, but he could actually explain how much light is present at all the different colors as function of temperature. And that formula was perfectly fitting with, for example, the fireplace you see here. It also fitted perfectly to the light you see coming from the sun. So if you take the sunlight and you split it into all the colors of the rainbow, but by the way, that's exactly what happens in the rainbow. It is the colors of the light from the sun that gets split out in different directions by raindrops. And there you see also this perfect distribution of colors that Planck could account for. But you see something more. You actually see that there are dark stripes. So this is what we call a spectrum, all the colors of light, and the intensity has a relatively smooth character, except from time to time, there are these dark stripes. There's about 100,000 of these dark stripes in the spectrum from the sun. And all these stripes correspond to matter that we also know on Earth. For example, these two orange stripes you see here, they come from sodium atoms. And if you take a car home tonight and you go on the highways, you might have these orange lamps, and they're actually orange with exactly this color because there's a sodium gas inside those lamps. And all these other stripes were also recognized as being the same colors as colors we have on Earth. So I could actually go on for the next hour and tell you how astronomers looking at every star in the sky know exactly what material is that star is composed of, because they can see all these stripes. But I don't want to do that, but I would like to tell you one thing, that there was a few stripes that people could not recognize. And then they figured that's maybe a new kind of material we just don't have on Earth. And they named it after the sun. So the sun is Helios in Greek. So this new material was called helium. And so helium had never been seen on Earth at 1855. And it was suddenly seen in this spectrum. So now we had this new material. And about a decade later, chemists isolated helium on Earth for the first time. So this is also part of the story, something that happened a little more than 100 years ago, this understanding of light. And the importance of these spectral lines, as they are called, cannot be underestimated for our friends, the astronomers, because they can compose the whole history of the universe and what is the development of stars, what kind of matter is created in the universe, where and when. But it was also raising, of course, another important question. Why? Why is it that sodium is having this orange light, and why is helium having some other colors? And the answer to that was given by a Danish scientist, Niels Bohr. So Niels Bohr was at first concerned about the light coming from a hot gas of hydrogen atoms. And that gas is emitting light, but not all the colors of the rainbow, but only very particular stripes, just like the stripes I showed you before. And to understand that, he took this idea from Planck saying that a given color is the same as a given frequency, which is the same as a given energy. So the hydrogen matters in some way to emit certain values of energy and not any other value of energy. And that led Bohr to a model of the atom. So what you see here is the famous Bohr model of the atom, which consists of a nucleus, which is very heavy and therefore at rest in this picture. And then you have a rapid electron, which is circulating around the nucleus, just like a planetary system. And this is, of course, taught in schools all over the world, this model of atoms. This model does not explain why you see special frequencies, because this electron can move around at various different distances, and therefore it will also move around at all kinds of frequencies. But Bohr, he made a crazy postulate, very courageous, a 27-year young physicist, and he claimed that in fact it's forbidden for the electron to be just anywhere. It's only allowed to be in this orbit or the second orbit or the third orbit, and there's an infinity of these orbits, but they are all at only very precise distances to the atomic nucleus. And just like the satellite in orbit around Earth, it costs so and so much energy to lift your satellite to this height. It costs more energy to lift it higher. And the difference between those energies is exactly the energy that would be released if you jumped from orbit number 2 to number 1. So Bohr makes the second crazy postulate. He says that this electron can be in one orbit and then suddenly it can jump to another one. And energy is conserved. That's a almost holy principle in physics. But if you go from a state with one energy and you go to another orbit with a lower energy, then where does the remaining energy go? And of course, it goes into the light. It goes to the emission of just this quantum of light. And since there's only these particular orbits, there's also only these particular energies. And therefore, you also only find these particular frequencies of the light. So Bohr's model is a model. It's not really a theory, but it's a model description of matter according to which you will only get particular colors of light. So that was very exciting and also very daring by Bohr. He was also able to make a formula. That's the most magic part of it. So he could actually give a simple expression that you could write down for what is the energies of these things. And he could predict, therefore, all the frequencies, also the ones that had not been seen yet. And these frequencies were predicted with about 5 digits of precision in 1915. So that's the first time in the history of science that you can make a prediction which is correct to nearly 1 in a million. And that was also true for Bohr's theory. Absolutely fantastic. So Bohr's postulates, as they are often called, they explain that all atoms emit light, and it happens at these very special frequencies. And I just remind you that Planck had called these units of energy for quanta. And this is why this theory is called quantum theory. It's the quantum theory of light, because light comes in these packages. And Bohr actually turned this into a quantum theory of matter, because also the atomic energies can only have these very particular values. There's a certain quantum that you have to get. I guess if you go to at least if you go to a Danish supermarket, they will often use the word quantum. There could be a discount if you buy a sufficiently large quanta of something. Here in quantum physics, it's the other way around. They are the small quanta of energy in the atoms. Now, to Bohr's dismay, when he tried to make this theory work on more complicated atoms than hydrogen, the helium atom, for example, is more difficult. It has 2 electrons in orbit. And when he tried to make the theory work, the precision was not nearly as good. So I got this enormously good precision of 5 digits precision for hydrogen. For helium, you are off by 10–15%. And there was no way. I mean, Bohr was, for the students in the room, you can probably imagine Bohr was using one student after the other to do these calculations. And it just failed and failed and failed. And it was people were ready to give up Bohr's theory in the early 20s. Then came around this French scientist, Louis de Broglie, and he said, maybe we got it wrong. I mean, maybe this idea of Bohr with the orbits is right, but maybe it's not a particle who's running around these orbits. Maybe what characterizes the orbits is some kind of wavy motion. Because you know that if you, for example, have a rubber band and you have it in motion, then there's no beginning and end of the rubber band because it's circular. So it has to bite its own tail. So you could imagine that this was a rubber band oscillating up and down. And of course, it can have an oscillation and a second oscillation, third one and the fourth one. But it has to always be like a multiple of entire oscillations when you go all the way around this ring. So de Broglie, he said, all these different number 1, 2, 3, 4, 5 orbits by Bohr, maybe they just show that there could be 2 of these oscillating regions, or 3, or 4, or 5. So we should not look for a moving particle. We should rather look for some wave-like pattern, like a water wave or a vibrating string. Just a wild guess by Du Bois, but physicists sometimes have to make wild guesses. And if it's true that it's a wave, the physicists are actually not on completely new ground. We have lots of theories for waves. The light is described as a wave. Water waves are waves. Vibrating strings are waves, and sound is also waves. And all of these phenomena had been described by theoretical physicists also in the previous century. So the task was to find the right physicist to try to describe these waves with equations and see what came out of that. So that physicist doing that was Erwin Schrödinger. Schrödinger actually later in his life lived in Dublin for a time, so this is almost like a local story. Ireland was actually always a hub for fantastic science, both in the classical times and in modern times. So here is Schrödinger at an earlier time in his life in 1925, when he was looking for this wave thing. And before I show you the equation to scare you, I just want to remind you that a wave is a complicated phenomenon. This is a water surface. And to fully describe this wave, you notice that everywhere on the surface, there's a wave, there's a height of the wave, and that height differs from point to point. Some places there's a trough, some place there's a little hill, and some place you just have an almost the same surface all around this thing. And this is just a picture. If I was to do a little movie, it would of course be moving up and down all over the place. So it's not really as simple as just a particle moving around. Here I have for every point in space to tell you how high is that wave. And this is why the equation gets a little bit complicated. Here is the Schrödinger's equation. So I don't want to do mathematics with you, but I just want to tell you that to scare off amateurs, we use Greek letters, because then we can keep it for ourselves. So the wave, the height of the water wave is here denoted by this cactus, which is the Greek letter psi. And what we are asking is, what is that as a function of position? So this is telling us where we are in space, and as function of time. So this is at what time we are asking for this function. And this equation tells how that function changes with time. So if I solve it, I will actually find a wave solution. And it's not any more complicated than the wave equations to describe water waves. They're actually much worse than this one, or sound waves. And we know exactly how to solve these equations. Schrödinger, he solved this particular equation for the case of the hydrogen atom. And these different pictures are what we call standing wave solutions. So they are solutions which are staying with that kind of spatial picture in time, just going up and down. You can probably recognize these ring patterns, which are very similar to if you drop a stone in a pond of water, but there are also more nice pictures or beautiful pictures down here. I always like to compare this with a more classical phenomenon, namely the motion of the surface of a guitar. So this is a guitar, and when you play it, then of course you play the strings, but the motion of the strings are transported to the body of the guitar. And this is the surface of the guitar measured with a police radar, the kind of radar they use to measure if you go too fast on the road, can also measure this very, very tiny motion of this guitar surface. So what you see here is actually how the left and right side of the guitar here are moving in and out of the body of the guitar. Of course, microscopic, so you don't see it with your naked eye. And when you play a higher pitch on the guitar, you see here 6 little areas which are moving up and down with respect to each other. And if you look at Schrödinger's beautiful solutions, you have also here 2 areas, and over here you actually have 6 areas, just like the 6 areas on the guitar. So this deep sound, long, big patterns of motion, high-pitched sounds, and small patterns of motion are equivalent to what we see in the atomic world, where these are the low energy states with the less structure, and these are high energy states of the atoms, which have the higher and finer structure. And the magic thing that happened was that Schrödinger solved this equation, and he found exactly the same frequencies as Bohr, which means he also found exactly the same frequencies as known in experiments. And maybe the most cool thing was that a Norwegian theorist a few years later did the same thing for helium with 2 electrons, and he found the correct values for helium to better than 3 digits. So now we suddenly had a theory that was quantitative and actually worked for all matter. So you would think that, wow, now we have a theory. The only thing that was missing was nobody had actually yet discovered what is this psi. I mean, it's just a mathematical wave, but it's not a water wave, and it's not a sound wave, it's not an electric wave. Nobody actually knew what kind of wave it was. And well, I don't know what happened here. I have to go the other way, sorry. So here's the first insight into this puzzle. So of course it was not John Travolta who told what is the interpretation of this wave, but Olivia Newton-John's grandfather was a German scientist, Max Born. Oh, there's something with my mouse here. Just excuse me for a second. Well, I don't know. I'm just apologizing for this. There's something here with my presenter mode. Well, just excuse me for a second. I just stop sharing and come back again. So let's see. So this is good. Try again. Let's see. I hope this works better this time. Yes. Okay. So here is Max Born. I apologize for this little fallout of the technology. So Max Born in the mid-20s, he made the observation that when you do experiments and you actually detect the microscopic particles, you detect them in all different positions from shot to shot, but all together they form a distribution who looks like these pictures. So Max Born, he made what we call the interpretation of the wave function, that the wave function, when we calculate it, gives energies, these are the vibration frequencies, out super precisely, but the location of the particle is completely random, but the wave function tells you the probability that you meet the particle this place or the other place. So it's a bit like tossing a coin. Every time you toss a coin, there's a well-known probability, most of the time 50%, to get heads or tails, but you cannot predict what happens in every single experiment, but you have these probabilities which are correct. So in the quantum mechanical case, we have a probabilistic description. Where do we actually see the particle? What do we get when I do a measurement on this particular particle? And this is exactly what has troubled scientists like Einstein, what is happening here. Let me first show you that it's correct. So when you take millions and millions of electrons and you shoot them through a small hole in a screen, then if they were classical particles, they would form some big spot on the target screen. But if you do it with electrons, they are actually quantum mechanical particles, and you should solve this wave equation. And what you find is a prediction and also experiments that give this beautiful ring pattern. So what you see here is a photographic film with lots and lots of little white dots. And every white dot is where one electron landed on this film. But if you form the whole picture of millions of them, then you get these beautiful rings which look exactly like waves. So the prediction of quantum mechanics says they should distribute themselves according to these wave patterns, and that's exactly what they do in the experiment. So you can do the same today with big molecules. So these are famous carbon-60 or fullerene molecules, big heavy objects, but still if you send them through this kind of experimental arrangement, the theory predicts that there should be this kind of wavy pattern, and the experiments, that's the red curve, also shows that indeed they follow this wavy pattern. So Einstein was not really happy about this. He was, for example, asking himself, what does it mean? Is the electron a wave before we detect it? Is the wave a real property of the particle? Or is the particle actually already in a given position? And this wave stuff is just something else we use to describe the whole phenomenon statistically. There's a small picture I've made here with an example of what such a wave could look like, the wave function could look like. And if the red curve means the probability to find the particle, then of course, now I do an experiment and I can really find it anywhere where this red curve is above 0. So let's say I do an experiment and poof, this is where I see it. Then if I do the next measurement, maybe it will be some other location. And if I do really many measurements, it will form a distribution that looks just like this curve. Now, it is a fundamental question, actually, if the particle was already there before you saw it, or if it only appeared there due to the measurement, and which is what most physicists believe today. Einstein famously asked once, does God play dice? And it's precisely this question he had in mind when he asked that famous question. Can it be truly random, or is there no way for us as scientists to actually predict what happens in the experiment? And I hope you appreciate that this is a unique situation for scientists. Normally our theories are actually predicting what to see in an experiment. They don't predict probabilities for what to see in experiments. If they do, it's typically because there's something we admit that we don't know. But in quantum mechanics, we don't even know what is the missing piece to make a better description. Here's another famous paradox proposed by Albert Einstein. If a wave is allowed to go through two openings in a screen, then of course the wave itself is also existing on the right-hand side, but waves, they spread in space. And what comes from the lower hole and the upper hole can meet. And when that happens, you see what's called interference. So waves can add or subtract their values from each other. And the prediction of such an experiment is a stripe pattern. So I already showed you beautiful wave patterns with rings shaped. So here it's just linear stripes in this thought experiment by Albert Einstein. But Einstein had this super good question. Every time I see a particle here, can I really not in any way know whether that particle took the upper path or it took the lower path? And Bohr, he made this constructed drawing with a door where he said, well, if you want to be sure that it took the upper path, you should close this door. But if you close this door, there's also no wave that can go through here. And then you will not even predict the stripes anymore. So Bohr made this claim or this argument that, in fact, the experiment where you want to see the stripe nature, the wave nature, is excluding the particle nature, namely which way. And if you want to know which way it goes, you won't see the stripes. So there's what he called complementarity. There's an inherent property in this kind of description of the world where you can look at things in different ways. No, not any one of them is the real right one. You would rather say that one fits to one experiment and one fits to the other experiment. Still, of course, Einstein's question is a good one. When you see the particle come here on the screen on the right, does it mean it went through both slit openings? Does it mean that a single particle can be two places at the same time? And that is maybe not the way that Bohr would phrase it, but it's actually the main ingredient in the quantum computer is this ambiguity, this thing in the formalism that describes the particles as if they are several places at the same time. A last little paradox by Einstein before I go to the quantum computer. In 1935, he and colleagues proposed this idea of having two particles who fly apart. They are both described by quantum mechanics, so they are both extended waves, so we don't know exactly where they are. But by laws of physics, they have to be at the same distance to the origin. So if I measure the particle on the left, the red one, and I now know precisely where it is, it localizes, instead of being the big wave, it is now in a definite position. The blue particle on the right also has to be in a definite position. And Einstein found that spooky. He said, this is a spooky action at a distance, because the fact that I do a measurement, maybe in one lab, maybe on one continent, has the consequence that a wave on the other continent is suddenly collapsing into a localized particle. So he really didn't like that, this physical idea that because of a measurement on one particle, something happens to the other particle. And Bohr, he gave a super long answer. I just show you here one fraction of the sentence. Bohr loved very long sentences. And here he says, of course, there's no question of a mechanical disturbance of this other particle. There is essentially the question of an influence on the very conditions which define the possible types of predictions, and the sentence go on. But what Bohr is actually saying is that when we do measurements in the physical world, we are not changing something in the physical world, we're changing our knowledge, we're changing our ability to make predictions. So what does happen here is that I see one particle and therefore I know where is the other particle. And the wave function, this psi that we calculate, is not a physical property of the particle, it's a description of my knowledge. And of course, you will maybe not so surprised that you can know something about another particle if you do a measurement on the first one. Bohr also said that these conditions constitute an inherent element of the description of any phenomenon to which the term physical reality can be attached. So for Bohr, physical reality is actually the predictions we make and the experiments we do. He doesn't even need a physical reality in the microscopic world. So if you meet a quantum physicist who looks frustrated, it could be because all the theory we do and all the experiments we do are on things that are not even real, or that we do not necessarily consider as if they are real. But it's still a fantastic theory. It's a theory that can make enormously good predictions for what the experiments will show. And that at least is what makes us use physics and describe the physical world by physics. And it's also why people who have strongly diverging views on the interpretation of quantum physics can still agree and build quantum computers together, because we all know that the predictions we make, the experiments we do, will come out the way that theory says. But what is really happening in the microscopic world is too hard to understand, or also for physicists to this very day. Now, Schrödinger, for example, he hated the quantum mechanical physics, the way it developed. And at some point he said, maybe we should never describe a single particle. There is no single particle who is being measured in a random precision. We always measure on billions of particles. And what we see are distributions. And those distributions are, as I showed you, deterministic. They are just the wave functions. Doing experiment on a single particle is just as crazy as the idea that we could raise the ichthyosaur back in the zoos. Now, this is Schrödinger 1952. As I'll show you in a little while, today we can easily do experiments with single atoms, single particles, and we actually do see in the lab this randomness all of the time. So just to finish the quantum physics part of this presentation, the physicists were really not in big trouble, but they were in big disagreement about quantum physics. Einstein said, if quantum theory is correct, it signifies the end of physics as a science. Schrödinger, he said, I do not like it, and I'm sorry I ever had anything to do with it. He didn't give the Nobel Prize in physics back though, but he was really frustrated having created this monster of a theory that did not properly describe, or maybe did not even recognize, the existence of a real microscopic world. And Bohr said that those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. So if you don't understand quantum mechanics, then I've done a good job, because nobody understands quantum mechanics. But it works, and that is really the maybe most crazy part of this. We do have a mathematical theory. We can solve equations. I can tell you energies with up to 12-digit precision. I can tell you probabilities, and they hold when we do the experiment in the lab. And now, for the rest of this talk, I will tell you how the craziest effects are now being what we want to use in the laboratory and in a number of future quantum technologies. So just to bring you immediately into this world where we now have the ichthyosaur in the lab, this is my French colleague, Serge Roche, and his colleague, Igor Dodzenko. And they are between two mirrors. They're catching single photons, single quanta of light. And they're creating those single quanta of light by sending single atoms through this arrangement. Because if the atoms enter with the electron in this outer state, then it can jump in, and then it can release exactly one quantum. And then those guys, they can catch that single quantum as a standing wave between those two mirrors. And then they can come with a second atom and a third atom, and all these individual atoms can absorb photons, they can emit photons, or they can just interact and in a sense measure what is the state inside this arrangement here. It's called a cavity. So what is shown here on the light is actually thousands of atoms, and if they come out in the low energy state or the high energy state, it's shown with a red bar or a blue bar. And you can see here's a lot of atoms coming out in the lower state. And then suddenly there are a few who come out in the upper state and then in the lower state again. And that is really the experimentalist watching atom by atom, one atom at a time, which state they are in. And they're also here watching that there's a new change happening to the amount of light inside this cavity, whether there's a single photon present or no photon present in the cavity. So the ichthyosaur is actually in the zoo of the physicist, and we can master them, we can control them, we can make this system evolve according to what we like it to do. And that has been a tremendous evolution in the last 20, 30 years of modern physical science. So quantum computer. Here is an old ad for a classical computer, a laptop computer of about 400 euro, about 3 billion calculations per second, about 3 billion bytes of data on which it can do these calculations. So these are fantastic numbers, super fast computers. And today in your smartphone, you have similar computing power. And the price, 400 euros. Now, what we're talking about is a processor type. We don't even know yet what's going to be the winning architecture. we would be happy if it could do 1,000 operations per second and not 3 billion like your smartphone or your laptop computer. Even 100 hertz, 100 operations per second would be fine. You have maybe billions of bytes available in your laptop computer. If we could get 1,000 bits, that would be great. And we would probably be able to pay up to 1 billion euros for a machine of this kind. And here's a candidate picture, my colleague Jakob Scherson, who is using trap atoms in a way to control every atom to be the data in the computer. But I'd like you to take just a look at these numbers, because we're actually talking about a device which is 1 million times more slow and 1 million times fewer bits, 1 million times smaller memory, and about 1 million times more expensive. So how can that be? I mean, the numbers fit, but they kind of fit in the wrong order. A slow and small machine who is very, very expensive. And that's where the quantum comes in. Because in classical computers, the unit, the numbers that we deal with are often used in what we call a base 2 or binary values. So every number can be written using only the digits 0 and 1. So that's writing it on paper. In a physical world, you have to have some physical property who knows if you're thinking about 0 or 1. In your laptop computer or your smartphone, it's going to be an electric voltage, or it's going to be some magnetization of some domain on a hard disk. I just draw here a little abacus where the beat can be on the left or right. And if it's on the left, it means 0. And if I move it to the right, it means 1. So this is my data storage unit. Of course, we don't use that in real life, but it's just to illustrate to you that here I have a physical system who can be 0 or 1. And for the physical system, it's not numbers, it's actually physical state. Where is the particle sitting, the beat sitting in this little abacus? So this can be 0 or 1, to be 0 or to be 1, or to be or not to be. That's the question, if I may quote Shakespeare here. The quantum computer is described by wave functions. So the little beat in the abacus, if that was described by this hydrogen wave function I showed you before, it could both be on the left and on the right. So here I've drawn it as if it is both on the left and the right at the same time, because the quantum mechanical microscopic particles are in some sense, different places at the same time. Not if we look at them, then they will have to make up their mind. But until we look at them, then they will actually have this capacity of being both left and right at the same time. So to be and not to be, that's the quantum computer answer to this. So this is a very basic idea. And of course, you have to work a little bit on it to actually make it work and do something useful for you. But if you want to have one message about quantum computing out of this talk, first you have the message from quantum physics. Particles are very strange in some sense. They can be several places at the same time if you don't look at them. And the second message is that in the computer, we use that because the memory of 0 and 1 can be 0 and 1 at the same time. So we can do a calculation with 2 inputs at the same time. Now, here's a picture of the largest computer in the world. It's based in China. It has 10 million of the processors you have in a normal PC computer. And just by building these many PC processors together, you can get a supercomputer. And this machine, doing, say, 3 billion operations per second on all these processors, it becomes equivalent to a 17-digit number of operations per second. So it's just a crazy amount of calculation you can do on these computers. Now, I want to compare that with my quantum bits. So if I have hundreds of these little abacuses here with a beat who can be both 0 and 1 at the same time, then this one is 0 and 1 at the same time. This one is 0 and 1 at the same time. So altogether, those two can be 2 times 2 possible things at the same time. And if you do that 100 times, you get 2 times 2 times 2, 100 times. That's actually a number with 30 digits. So when I'm using this as my data in my computer, and every bit can take all values at the same time, I'm actually doing a 30-digit number of calculations per second if it takes 1 second to do a calculation in this machine. So you can see, even though I have only 100 bits, and even though my machine is slow, I can actually do many more calculations than this supercomputer out in China. And the reason is that all these fantastically many operations it's doing, it's still only one number at a time. It's a large many-digit number, but it can only do one at a time, while this one is doing all the candidate guesses at the same time. And 100 bits is 2 times 2 times 2, 100 times, is a huge number. It's more than the number Oh, it's not more than the number of atoms in the universe, but it's a huge number. So this is why this small and slow processor with very few bits is actually able to beat these monster computers, even when it's slow, if you can find the proper calculations to do it on it. So this is a proposal that goes back to the 1980s by famous scientists, but they were challenged with what you can actually do with it. So as I told you, we use that the bits have values 0 and 1 at the same time. We do essentially the same calculations as we do on the classical computer. All the same basic operations that happen inside electronics in a normal computer are now being done, but the physical system we act on can have the values 0 and 1 at the same time, or many bits can have all these huge number of different numbers at the same time. So you do this in parallel, just as well as if you had a lot of parallel computers working for you on different inputs, but it can all be put in one and the same hardware. So for example, imagine you had a pocket calculator who could calculate the square of a number. You type in 6, you push the square button and it calculates 6 squared, which is 36. Then you push in 7 and you get 7 squared, which is 49. If it was a quantum computer, you could punch it 6 and 7 at the same time. And then it would give you 36 and 49 at the same time. Or you could punch it all possible numbers at the same time, and it would give you all the numbers squared at the same time. So crazy, but this is actually what quantum mechanics does. And I will immediately tell you why it's also a bad idea, because here is 36 and 49 at the same time in my quantum computer. And now I want to know the answer. Of course, I have to get the number out of the machine. And on a pocket calculator, you look at the display and it says the number. The same way I actually have to look at my quantum computer. And when I look at the bits, then this randomness happens. So instead of actually reading both 36 and 49, by accident, every bit decides to be 0 or 1. And I'm going to read the number 36 or the number 49 instead of 36 and 49. So this God playing dice of Einstein is really a serious threat to this amazing idea of the quantum computer. It may actually have gone through all the labor of calculating all these fantastic numbers, but when you read it out, you get a random answer instead of all the answers at the same time. So this was really also realized in the 1980s by Richard Feynman and others, that maybe the quantum computer was a funny idea, but it was not more than a funny idea because of exactly this readout problem. And the story could have stopped there, but in the mid and late 90s, quantum algorithms were invented. So there were people looking into what kind of mathematics problems we could still solve by this machine. So this idea that you have to read out many numbers, that's a no-go, because you will collapse the computer to give you only one classical number in the end. But then mathematicians look, what about problems that need that you do a lot of calculations, but you're only interested in one answer at the end. So one of those problems was promoted by Peter Shaw, a really hard problem, but with only one correct answer. And his problem was of this kind. I give you here number 2257, and I ask you which two integer numbers should you multiply together to get 2257. So you know that if you should answer this question, you could try. Is 2 a factor? Is 3 a factor? Is 4 a factor? Is 5 a factor? And if there is a factor, a number who would fully match in this equation, then you will hit it at some point. So you have to try many times, but you're not interested in all these wrong answers. You're actually only interested in one particular number, namely the factor that will factor 2257. Or in general, you have a huge number n, and you want to write it as a product of two numbers, x and y. Please find x and y. Very, very complicated mathematics problem, but the answer is going to be one answer, and you can also easily check if the answer is the right one. So to make you stop worrying, 2257 is 37 times 61. So you would have to try until you reach 37. But Peter Shaw said, how about asking a quantum computer this problem? Could we imagine that we gave an algorithm that could actually help find this and only that number 37 coming out of the computer as the result of a calculation? And Shaw developed exactly what we call the Shaw algorithm, who is solving that kind of problem for us. So the quantum computer can do that. And if you go to really big numbers, not 2257, but numbers that have to be written with hundreds of digits, then you are in a problem class where it will take years or even millions of years to solve them on the computers we have today, while the quantum computer is estimated to be able to do this kind of calculations, even in just few hours, if they can do operations at that fairly modest speed that I asked for just before. And it's not because the computer is fast, it's because it can actually try all the candidate values at the same time, so to speak, because of this massive parallelism that is offered in quantum mechanics. So is that worth $1 billion? Because I was also putting a price tag on the quantum computer. Well, that might actually be the case. There are some ideas using these numbers for codes. In fact, when you use codes on the internet, it's very often based on that problem being difficult. So, I mean, if you could actually easily find factors in big numbers, you could break internet security as we use it today. So the espionage agencies, the National Security Agency, for example, supported quantum computing research heavily from the beginning. I was at an NSA conference in America and just very, very related to this topic. In the same morning in 2004 or 5, there was a newspaper where they introduced the new big American missile armed submarine, USS Jimmy Carter. And of course, you look around into this article, it's very exciting, but the headline says that it's able to tap fiber optic communications. So, I mean, we can forget about all the missiles. The most important thing to tell us about this thing is that it can tap undersea cables and eavesdrop on the communication passing through them. And therefore, it is capable to perform missions vitally important to the war on terror. So the Americans have built a submarine for billions. And at that price, they have a machine who can actually go down, find the optical cables at the sea bottom, and they can get messages out. But if they are encrypted, of course, they don't know what is in that message. So therefore, they may also want to spend another billion to be able to actually break those codes. So there's actually definitely interest in the kind of tasks that quantum computers can do. And in the beginning, it was very much military and intelligence. But now, of course, there are also other applications. Here's a picture of Angela Merkel. There was a big scandal a few years ago that the Americans were actually eavesdropping on her phone, but it turned out that the Germans were also eavesdropping on Barack Obama's phone. So I mean, they're all good friends and they are all listening in. And if you use encryption, you might actually have this kind of math problem you would like to solve. There's also other problems, what happened here. But before I get to the other problems, let me just tell you a little bit about what we do then, because that's fortunate for the physicists. We actually don't have to reinvent the computer. The way the classical computer works can be copied to a large degree into our quantum computer. And your classical computer can only do very, very simple and basic things. It can take one of these data values, which are 0 and 1, and then it can either leave it alone or it can change it. And changing it is called not, because if you do not have 0, you have 1, and if you do not have 1, you have 0. So maybe you have this quantum system, or you have a classical system who represents a 0 and 1, and then you may want to do this not operation. And that is one of these things you do billions of times per second in your computer. The only challenge for us now is that I want to do the not operation on a thing where I don't even know if it's left or right. So of course, if it was classical, I would look, is the beat to the left? Okay, it's on the left. I move it to the right. That's exactly the not operation. But if I'm not allowed to look, can I then actually turn 0 into 1 and 1 into 0? And fortunately with PowerPoint, I can, because I can just rotate the thing, right? So you can see here that whatever was on the left side is now on the right-hand side. Whatever was on the right is on the left. So in fact, even if I have both left and right, it will become both right and left due to this operation. So if the real physical system that I'll show you in a second can be just rotated in this way, then we can actually do these 1-bit gates. Now there's another component in your computer. It's essentially what we call a transistor. It's a device where one voltage can control what happens to another voltage, or one current can control what happens to another electrical current. So we need to do addition of numbers. We need to have the different bits control what happens to the other bits to do real calculations. So what I show you here is how the left abacus should control what happens to the right one. And if the left one is 0, the operation called controlled not should do nothing if you are 0. So I just do nothing on the right-hand side. Control is 0, target no change. But if the control particle is in the one state, then I should flip the right-hand side. So now I show you I can do that, just as I did before. So this is the easy part. Now comes the difficult part. What if the left one is both 0 and 1? Because if that's the case, then the right one should both be not rotated and rotated. And now PowerPoint has to give up, but I also have to admit that I'm not using a quantum computer here. So now we have to dive into the microscopic world and find physical microscopic particles who can both be at several places at the same time, but they can also control what the other particles are doing in the way that I'm just requiring here, but where I have to give up in PowerPoint. So there's been a lot of people thinking about how to do that. So I showed you this picture of my colleague before. He's actually trapping individual atoms. So all these yellow dots is one single atom, and they are sitting so close to each other that he can actually either put them on top of each other, or he can induce forces between them so that one particle is doing some dynamics which can be controlled by the guy next to it. I will not go in detail, but just tell you that this is something we can do with the atomic forces. Here you have also atoms, but we have stripped off an electron from the atoms. So now they are electrically charged, and they can also be trapped, holding position because they repel each other. And in this trapping arrangement, these individual atoms, so every dot you see in this picture is actually just one atom, they can also control the dynamics of each other. This is the first quantum computer who actually computed something. This is a molecule. So this is a model of the molecule, the picture I show you here, but molecules consist of little atoms who are sitting in configurations with respect to each other. And these little atomic nuclei, they all have a property that's called spin. They react to magnetic fields, and they can either point up like little magnets themselves or down. And this is the 0 and 1 in this little computer. And you can steer their motion with radio waves. This is exactly what they do in hospitals when they do magnetic resonance imaging. They're actually making these little arrows rotate, and it takes a very particular frequency to make any of them rotate. If a neighboring one is pointing the same way as you do, then it can change that frequency. If it points the opposite direction, it can change the frequency in the other way, just the same way as you know that magnets can repel or attract each other. So this little molecule could actually do the equivalent of calculations on up to 7 bits in a quantum computing about 20 years ago. There are crystals that have atoms inside of them where you can do the same tricks as with the atoms in the experiment I showed you. There are circuitry, electronic circuits now, which can even have currents that are running around in this quantum manner, because we can take that circuitry and cool it down to ultra low temperatures and isolate it very well. Here's a version of that circuitry also that we have been looking at in my group. So there's a number of candidates around where we use microscopic forces between microscopic particles to actually have particles who can be 2 places at the same time and can control each other depending on which states they are in. And it works amazingly. So who will build this kind of machine? Well, there's a lot of people who like to have such machines, and this is a list of private companies who are right now actually building these kind of devices. So Google is famously making one, IBM is making one, Microsoft is working on it, Intel, Chinese company Alibaba. This list is a list of companies who have it's not under the name of BlackBerry, but the BlackBerry phone generated a lot of funding, which is now being used towards building quantum computers. There are also, of course, national initiatives in America and China and Canada, in many countries. And Europe has a big flagship project, which is running currently, which has a 1 billion euro funding into this kind of technology. So scientists and companies are working together, and there are scientists who spin out companies from universities to build these fantastic devices. So how far have we come? Well, what I show you here is 2 pieces of lab equipment. The one on the left is one of these superconducting circuit machines. It's mounted in this very special way because it's going to go into a big barrel and cool down to minus 273 degrees. And so therefore, when it's out of sight, you better make sure that everything got on the inside before it went into that big fridge. What you see here on the right is an experiment with trapped atoms. So here's Chris Monroe from the United States, and he has lots of lasers, and somewhere he also has his atoms flying around. This is a few years ago. what I show you here is Google's chip. And this is a chip that looks like any modern computer chip, but this is a quantum computer chip who has a number of these quantum bits that I showed to you, up to more than 100 bits in the current version. So everything is beautifully manufactured. All these little wires make the connections to the bits inside the chip, and this chip then has to be cooled down. And Chris is similar on a way to something very pretty and beautiful. This is also a chip. Inside this chip, there are wires who make electric and magnetic fields, and just above the chip surface, and here's a magnified view, you can see 50 or 51 little blue atoms. So this manufactured and very, very pretty chip is a way for every user in the world to buy that chip, and then you can almost guaranteed have this string of atoms on which Chris then has protocols to make these atoms do his calculation for him. So these are getting more and more close to commercial services. They are working more and more reliably every year. This is a machine, it's called D-Wave. You can actually buy it, and you're not supposed to open the box. It comes ready-made, and you are just using it from the screen and keyboard outside, and then it does the calculations for you. So this has the superconducting technology inside. Chris machine, you can also access online, because Amazon is offering a quantum computing web service now. So you can actually subscribe on Amazon to computing time on this particular ion trap quantum computer. And the idea of Amazon is actually to offer access to competing strategies, to competing architectures, and sitting somewhere in the real physical world, of course, in laboratories, but you can go and do calculations on these devices. What is the status? Well, the status is that we don't have interesting quantum computers for anything. We have computers that can do between 20 and maybe 150 quite good bits, which means that they don't make many errors. They are quite reliable, but not completely reliable. And on so small machines with an error rate of just 1.1%, you can actually not calculate anything that you cannot calculate on a classical computer, except there are some, say, useless tasks that are very hard to calculate, and where we can actually demonstrate that this machine can do it. So it's maybe not interesting physics or interesting mathematics we do, but we can run the machine, and whatever it does is very hard to simulate. That's maybe a more proper way to say it. There's also the bigger machines with many bits, but they are even worse quality. So therefore they cannot really not calculate anything of interest to us yet, but there's a hope that they might be able to solve, if not mathematics problems, then some more practical problems. What is roughly the minimum of some function? What is roughly the best strategy to do this or that task? It may be hard to prove that you could not do this with a normal computer, but if you didn't do it, then of course these machines will come with an answer that the buyer can actually, the consumer can actually use. So this is the quantum computer where it is. It's a machine who 10 years from now will be better, faster, stronger, and will, I'm very sure, have moved into the regime where it does useful things for us. Will we keep doing this for the next 10 years, and will we actually get that machine? When will we see any return from these technologies? And I'd like, as the last science slide in this presentation, I'd like to share with you a consideration about present day's computers. Because the chip that you have today, the size of a fingernail, running billions of calculations, that's not how the integrated technology here looked from the beginning. In 1947, the transistor was invented. There's 1 billion transistors in this chip. The original transistor was few centimeters in each direction. It was a fairly big device. It was super costly to make, and it was not clear at all how compact they would be and how expensive they would be. But today we know, of course, that you can actually get billions of them for a few $100s. But this long time span, were there any successes along the way? Is there anything useful you can do with just one single transistor? And I think there's a fantastic story to be told here, because a single transistor device, the one that this lady is holding in her hand, changed her life and millions of lives to the better in the early 1950s. So she's actually holding in her hand the first commercial application of one single transistor. And I'm not talking about the transistor radio. It's actually hearing aids, because the transistor has this ability to control one voltage or current by another one. And that's exactly what you want. You want a weak signal to control a strong current, so you can have an amplification of the sound signal in the hearing aids. So transistor is famously known to be an amplifier, and amplifiers before 1947 would require 6 kilograms of batteries, while this little device here actually required just normal batteries. So hearing aids is to this very day a very good example of what you can do with transistors, and of course today with really many transistors. It is my dream, and actually something that dream I share with many colleagues, that these little early stage quantum computing devices could be similarly used as very sensitive detectors, very sensitive amplifiers of signals. So one of the big columns in the European flagship project for quantum technologies is what we call quantum sensors. Devices who can measure very fast, very reliably, or very precisely, or very, very weak signals, and bring them to either material science, food safety, because you can detect toxics in your milk or whatever, military who can see or hear planes coming from long distance. There are many, many applications of sensors in modern society. And I just want to finish with that remark that may not need thousands and thousands of bits, but it may benefit enormously from this quantum technology. So it's about time I finish. I like to finish with a quote by Niels Bohr. Niels Bohr once said about quantum mechanics, and I think it's also true for quantum technologies and the whole talk I give you now on quantum computing, if we fail. Well, if we should one day wake up and realize that it had all been only a dream, then I'm absolutely sure, absolutely convinced that we would still have learned something. And I think that's definitely true also about the quantum computing. If it failed completely, we have learned so much about the quantum world. And I hope in this presentation that you have also at least some message you could take away from this talk. With this, I'd like to thank you for your attention.
Great. Thanks, Klaus, for the really, really nice talk. No, that was really clear. I really enjoyed it. So we have a few questions coming in, but yeah, don't be shy. This is your chance to find out about quantum physics. It's now or never. Okay, so I'll just start picking out a few, and I can read them to you, Klaus.
Yeah.
Okay, so one question asked, how is a quantum computer posed against Moore's law? Is it going to invalidate it, or is it just going to move the goalposts?
I think that in a real world, it will at most move the goalposts because for practical reasons, there will always be probably a limit that we will hit. But it's a completely new paradigm that we are exploring here. So it starts out being a little bit crazy that we don't need 10 times more bits, which is what Moore's law was doing. It was assuming that the number of bits would increase every 2 years. There would be an increase in the number of transistors on your chip. And we're actually going the opposite way. We're going for fewer bits, we're going for slower operations, but then we are using this new parallel thing. And that in itself gives such an enormous boost to the computational power. And I understand the very good question is, will that also be scalable to grow to even bigger size? And there will be, I'm sure, the same Moore's law who will restrict the number of components on a certain area. And there will be the same Moore's law in terms of how fast your operations can be. But you still have to remember that 100 bits, one operation per second, was billion times faster than the biggest computer in China. So yes, there is probably also a Moore's law for physical reasons, but we have explored a regime where the computing power scales insanely with even the small number of bits we have. Okay, great. Okay, another tricky question for you. It asks, is the wave function a real thing? I've read that there are two views, one where it is about what we know, and one where it is a real physical thing. Yes.
And then they ask, which do you believe? Which I
yes.
think is
yeah, just to restrict that. So there's about 21 different interpretations of the quantum mechanical wave function. If you really look into details, Bohr's view, the Copenhagen interpretation, is that the mathematical formalism is about our knowledge, and the wave function is our knowledge. Some alternative descriptions say that there are extra things. So the wave function is just some mathematics, but there is a real something also. But they will actually still treat the wave function as not as the physical object, but as a knowledge thing. And then there are, I think, a diminishing population among physicists who think that the wave function itself is the real thing, except for the very large number of physicists who think that everything is part of the same wave function, what we call the many-world interpretation. So sorry for making the long answer to a brilliant short question, but the problem is, of course, if the particle is everywhere, then if that's true, then I should also measure it everywhere. And then I should tell you, Steve, and you, Anthony, that the particle is to the left, but I should at the same time also tell you that it's on the right, because it is both on the left and the right. And that is actually also a consistent view of the world, that all these parallel realities exist at the same time. So that is the consistent view of wave function being physical, but it invites the physicist, the spectator, to be part of that big wave function. And that is in brief what the many world interpretation is about. That is treating the wave function as real. But my personal view, they all give the same predictions more or less. And so I like the aesthetic, minimalistic value of the Copenhagen interpretation. So I'm actually a fan of the wave function being a representation of my knowledge about the system.
Okay, very good. Okay, we have another question, which is interesting. Can quantum sensors help in searching for gravitational waves?
Yes, that is very likely. Of course, we already have gravitational waves detected by a big machine called LIGO and also other machines around the world. And I just want so it's a very good question. The sensitivity of these machines has to be enormous. And they are actually big mirrors which start oscillating when a gravitational wave comes by. And you're probing that by scattering light on these mirrors. And we know in optics and what we call quantum optics that we can actually make quantum states of light, which are more sensitive. It's not exactly a quantum computer, but it's the principles of quantum mechanics that help us and will help the next experiments on LIGO actually reach even better sensitivity. So we call it quantum LIGO, and I think already next 2 or 3 years, we will see the first experiments being done with quantum lights in LIGO. And there's a number of principles for quantum precision measurements that are using more fancy aspects of quantum light and quantum sensing, which will, I'm sure, also be employed in LIGO. It was a kind of joke, if I may tell you, when I was a student 35 years ago, I heard talks and people said, and then we will build this gravitational wave detector. We are 1,000,000 times away from the sensitivity it takes to see gravitational waves. And then they explained how they would get all the way down, and they would always miss a factor of 2. And then they could get that factor of 2 from quantum effects. And of course you can ridicule it, but if you build a machine at €1,000,000 or €1,000,000,000, sorry, and you by adding 1 million, which is a tiny fraction, can get a factor 2 precision, of course it's worth it. And a factor 2 precision on LIGO is the same as doubling the universe in size, because you can see things which are much, much further away. So it's actually a minimum investment to put the quantum technology on top of LIGO, and it's happening.
Okay, I didn't even know that. Okay, great. I'm asking these slightly out of order, and I'll just summarize by saying there's lots of thanks and telling you that there was a very interesting presentation. It was very clear, but I'll cut the rest of them out now. So someone is asking, how do you extract the answer from a quantum computer? So I presume after all the computation, and then you want to get your final answer at the end, and it's in this big maybe superposition. How do you get the answer out?
Yes. So that is specific from system to system. And in fact, any proposal for quantum computing has to deal with preparing the system in an initial state that you know, doing the gates, which I explained a little bit in my talk, and then do the readout at the end also. The good thing about the readout is that you are allowed to destroy the system in the readout. So I mean, at the very end, you don't have to keep the quantum state alive. You just want to know, is it in the one state or in the other state? So let me take the atom, for example. If I use the Bohr atomic states as my qubit, which is the lowest energy state, and the qubit 1 is the highest energy state, then I can just look at the atom and see if it emits one more quantum of light. And if that quantum of light comes out, it will signify to me the atom was in the upper state, which was the 1. And if it doesn't give me that quantum of light, it's because it was in the lower state, which meant 0. So at the very last moment, you have to find that way to look at your system. And when you look at that system, and you can do it with sufficient precision, of course, then you can actually read if the value is 0 and 1. And after that, there's no quantum state anymore. Then you have to reset the computer and run it again. The superconducting circuits I showed you, they are being probed by microwave signals who get reflected from the device. And depending on 0 or 1, the reflected signal will have one or another value. So it's done by physical methods, because after all, we have to see if the physical system is in one state or another. And we can often probe that using, for example, light or microwaves.
Okay, great. Someone is mentioning that they live near CERN, and they're interested about, you were saying, all these strange parts of quantum theory. I'm somewhat summarizing. And they ask, how important is the basic research going forward, especially particle accelerators in CERN? And I guess my interpretation is in terms of uncovering the strangeness about quantum mechanics.
Yes. So I think, I could only give a little glimpse into what quantum mechanics could do for us. And it was created by Bohr for the hydrogen atom, and for atomic physics, it has been a huge success in terms of precision and what it can do. But it actually also set the frame for all the other physics we do. So it's the same equation I showed you, the Schrödinger equation. If you want to describe a particle physics phenomenon, you set up the same kind of equation. And by a touch of magic, that theory is so correct that if you add few components to it to account for special relativity, to account for special properties of particles, it still works. And it more than works. A famous British physicist, Paul Dirac, he manipulated the equation and he got solutions he had not even dreamt of, solutions with apparent negative energies, pairs of solutions instead of only one solution. And then when he thought about it, he came up with an explanation. This could be antiparticles that corresponded to the negative mass. So the quantum mechanical formalism has actually given us things we did not even ask for. And within the big area of quantum particle physics, there are mechanisms that describe the interactions between the particles, which suddenly, by inventing one more particle into the formalism, you can explain how all particle masses appear, for example. There's something called the Higgs mechanism. And I think it's a wonder. So I'm not a particle physicist myself, but it's a wonder that fantastic theorists a few decades ago took the same kind of equation and said, with one single extra term, I can fix the whole world of all particles. But that single term has to be a particle. It has to have a weight around so and so much. And then at CERN, they launched a big campaign and they found that particle. I mean, it is a wonder of nature that it can be described by despite everything, so simple math. And so the largest campaign that was at CERN for the last decade was this search for this particular magic particle Higgs, which was just born out of the quantum mechanical formalism and was then confirmed to be there. And in some sense, you may admit also that if a theory makes a prediction of something that was never seen before, and you go and look and you find it, that's a super convincing evidence that there's something strong in that theory. So what particle physicists are now looking at is now the nature of that particle, and is it itself composed of other particles? So of course, particle physicists will never be satisfied. They will always have to dive in and see, is this something which is still then made of something else? And you will never be satisfied, right? Why does that particle have then that mass? Is that because of some underlying theory? But so far, the quantum theory, very much in the spirit that I described it here, has been the guiding star in asking the next good question also in particle physics.
Yeah, this is the theory that kind of refuses to be proven wrong in a way.
Yeah, in some exactly. That's a very good way to put it. I'll see if I can remember that. That was really good. It refuses to be proven wrong.
It really, yeah, it doesn't give up. Okay, there's loads of great questions coming in. Someone is asking about real world applications. So you mentioned quantum computing, you mentioned quantum sensing. They're asking here about AI and robotics.
Yes.
And then in particular, they're talking about, everyday applications that would benefit from this kind of computing.
Thank you very much for that question, because I had a little problem with my computer mouse. So the computer quantum can do much more than factoring numbers. So that's the thing I mentioned here. Factoring numbers is part of a mathematical thing having to do with what we call group theory. So it's actually the same as finding what we call hidden subgroups in mathematical groups. That's interesting. It can help search databases for the right element. So again, a question with many questions, but only one right answer. It can also perform fast machine learning, artificial intelligence, at many different levels, actually. So just to answer to that good question by the person who asked the question, in AI and machine learning, there are some algorithms used today that solve a very particular mathematical problem. And exactly that mathematical problem is extremely well suited for quantum computers. So there's a particular type of linear algebra you have to do, and quantum computers can do just that very well. So that means they can actually be used as a co-processor, helping you in a machine learning task. But there's also a more daring proposal that you could actually use the quantum computer itself as the machine learning thing. So it's the quantum computer who itself becomes the artificial intelligence. So, you know, that's two different things. One thing is to aid in doing a mathematical operation for something which is classical math, classical formulas. But the other thing is to actually use the quantum computer as the new artificial intelligence. And there are also ideas for why that could be efficient. It could learn faster. It could have the same information stored in a much, much smaller unit. And it could process what looks like a long-term memory with much fewer memory bits than a classical computer. So there are many people interested in machine learning with quantum technologies. And then there's a whole bunch of physicists who are interested, because in a very primitive level, the quantum computer itself is a very complicated physics system. And in a very analog sense, my bits interacting with each other could mimic real particles actually interacting with each other. And in fact, I do build it by having real particles who are already interacting with each other to be the bits. So you can actually play molecular quantum chemistry on a computer, either in this analog manner where you just make a physical system who looks like the real one, or you can also encode the equations that are so hard to solve in quantum mechanics and that the quantum computer solves them. Quantum mechanics is difficult. Quantum mechanics is difficult because the particles are described by wave functions who are everywhere at the same time. Why not use a computer whose data can also have different values at the same time? It is really the best possible maybe application of a quantum computer is to do quantum calculations. So this is why I mentioned here particle physics equations and quantum chemistry. But then of course on the more hyped part of it, of course, we think it can do everything. We could optimize traffic control because that's some optimization problem, and you could try different solutions at the same time and pick the good one. There was a physics conference a few years ago in Spain where the local bus authorities claimed to have used a quantum computer to optimize the airport bus. That's nonsense. Well, sorry, Sevilla, but I don't believe in that for one moment. but maybe in the future there are famous logistic transport problems where it is definitely within what we think quantum computers can do.
Okay, great. So the bus routing famously debunked here.
Well, I would say, of course, I'm just an angry old man. Maybe they used it. I cannot say.
Yeah, I think what I've heard is plane scheduling for the runway. So this is
yes, and there are many of these problems. Famous traveling salesman problem and other logistic problems. You could also imagine that a quantum coprocessor in a classical computer could help route the data inside your computer in the optimal way, and many design processes. If you have a GPS system, I mean, how do you find the fastest route from Dublin to Cork? Well, maybe there's a main road that it's evident, but your GPS will try all kinds of turn left, turn right here and there, and then it will find the shortest one. And a quantum computer could try all at the same time. So it is an exciting perspective, of course.
Mm-hmm. Okay, great. So there's loads of questions coming in. I don't know whether we get to them all, but someone is asking, basically, you had mentioned this code breaking ability with quantum computers, but now they're kind of asking the reverse. They're saying, okay, if you did have this quantum computer compared to a classical computer, you know, is this susceptible to security issues? Are there kind of ways of attacking a quantum computer?
Yeah. So I would say, of course, right now we are using also the quantum computers. The ones on Amazon will be on a normal internet with normal password protection. But there are colleagues who are very much concerned can you actually make safe quantum computing? And we do have strategies, so you can actually make a guaranteed security that I can even run my program on a colleague's quantum computer with a guarantee that he cannot mess with the data, right? He cannot learn what I asked the computer to do, and he cannot learn what answers it sends back to me. And that's related to what another aspect of quantum technology is called quantum cryptography. So this particles being both left and right can actually also be used for coding secrets in these days. You put them in a particular way, and the legal recipient has to read that measurement in the right way to get the right information out. So that my cheap answer to the question is that if somebody buys a quantum computer to break my codes, I will switch to quantum cryptography. And I'm the kind of person who can sell you everything. So first I sell the gangsters the quantum computer, and then I sell all the good guys quantum cryptography so they can protect themselves. But I also understood the question that it went deeper, because it was also a question about are the quantum computers themselves safe? And I think that safety is at least something that many people are not worrying about, but there are many proposals to make the quantum computer results and the quantum computer data 100% protected against adversaries. So people are really thinking about it, and there are good solutions.
Okay, there's a question, is quantum communication faster than the speed of light? Can you explain this?
Yeah, it's not. And it's a very, very good question also. There are indeed quantum communication that happens by means of those pre-shared particles. So I could have one particle on my side and one particle on your side. I can measure my particle, and that immediately has consequences for what you will get when you measure on
I should have combined this. There's also people asking about instantaneous communication.
Yeah. So the funny thing about that experiment is that I have not been able to communicate anything to you, because the particle you have in your hand was 50-50 before the measurement for being here or there, for example. And when I measure, there's a 50-50 chance that I will know that it's left or right. And when you look at it, it means that there's still 50-50. And because it's random what I get as a result. And therefore, even though I know your result, I cannot communicate to you what it is, except if I grab my phone and call you and say, it's on the left. And in all the quantum cryptography communication protocols, in fact, all communication protocols using these long distance correlation effects, there is a classical communication element where I have to tell you where to look or what to do or how to interpret what you measure. So it's true that in this formalism, it seems that something happens to your particle, but you can't see the difference. Let me put it the following way. I have a coin here between my hands. It's a quantum coin. So it is both heads and tails until I look. Or is it heads or tails before I look? Well, let's look. It's heads. But how can I know what it was before I looked? Because that's not possible, that task, right? So there's no way for you to see if I have done my measurement or not, because you will see something random, and precisely what you see is correlated with what I see, but we will only know when we talk on the phone, and that's sub speed of light. It is called sometimes the peaceful coexistence between special relativity and quantum mechanics, because in some sense, it's actually a miracle that quantum theory does not violate speed of light, because it does not even know the speed of light, but it actually happens. There is no instantaneous communication.
Okay, I have that phrase is new to me. So, okay, so there's still loads of questions coming in. I don't think.
If I may tell you one thing, just an anecdote.
Yeah.
The CIA and big American companies in the hippie times of the 70s actually supported hippie projects using LSD and other things to see if people could have a communication, allegedly because of quantum effects. But I mean, definitely people taking drugs, they felt some kind of common phenomena. So there were conferences where you were supposed to be naked all the time and sit in pants and discuss physics. And very famous physicists participated in those conferences. And it was literally supported from different agencies in America. Some of the ideas were debunked. There's a famous paper by a theorist called Wojciech Zurek, and who proved something called the no cloning theorem. So he just said, look, the quantum formalism does not allow us to copy state, And actually that immediately debunked a lot of these faster than light communication ideas. But CIA for a moment believed that their agents could be using teleportation and quantum correlations to maybe communicate with field agents instantaneously without telephones. But that was only for a couple of years.
Okay. That's also new to me. I'm learning loads tonight as well. Okay, so there's still loads of questions coming in. So I might just ask one more just to pique my interest, and then just to be respectful of Klaus's time, we might try and wrap things up. Someone is asking about entanglement, and they're asking, is it a man-made phenomenon, or does it ever happen by itself in nature?
Wonderful question. I think it happens all the time by itself. And the reason that we don't see entanglement because it's very difficult to preserve and protect and observe, therefore also, is actually typically because of more entanglement. So entanglement is that your particles get correlated with each other in a very intimate way. If this one is up, this one is definitely down. If this one is down, this one is definitely up. And both possibilities are present at the same time. How weird can it be? Now, if this particle met another particle and got entangled with that one too, and all interactions tend to entangle you in this quantum world, that's enough to ruin its connection with the first one. So entanglement happens always in the microscopic world just due to the forces between particles. They will bump into each other, and just take two balls who hit, one is kicked down, the other one up. But in quantum mechanics, it could be the opposite. So that simple collision will create entanglement because all possibilities are explored at the same time. So entanglement is everywhere. The electrons, if you have a helium atom with two electrons inside, they are entangled with each other. But it's not very interesting because they're also sitting almost on top of each other. As soon as you try to take them apart, then you have to make sure they don't bump into anything else. And the way you take them apart, you should also not make them entangled too much with your apparatus, because then they can only be so and so entangled with everybody else in the world. We even call it entanglement monogamy. So, like the same way as you're only allowed to have a single wife or husband, you can also only be maximally entangled with one other particle and not with two or three.
Okay, great. Yeah, great answer. So yeah, there's still loads of questions, and just apologies to everyone we didn't get to, but I guess we can't get to everything, and they're still kind of coming in. So just to say it again, thanks so much for your time, Klaus. We really appreciate it. The talk was really wonderful. It was really clear, and I learned lots during the discussion as well. So Steve, Professor Steve Campbell at UCD, maybe you want to say just a few words, just to close.
If I may say one thing before, Steve. So I just thank you very much for the invitation to give the talk, and thank you very much for the many excellent questions. I think many of the questions have a smell of good physicists behind them too. So unless you're already inscribed for physics studies or professionals, then please consider making physics your career. I mean, you can see there are many challenges ahead of us, and this is a field which is very welcoming to new talents. And if you're asking this kind of questions out of your own head after this single talk, I think we have good jobs for you in the future. So with that, I would like to thank for your attendance to this talk.
Yeah, I just also want to echo what Anthony has said and everything. Just thanks, Klaus, for the time, for the wonderful talk. And the questions coming in, it's great to see the amount of interest and activity from everyone from the talk. And so just for those, since we didn't get to everyone's talk, I just point people at the center that we have here in UCD. So I mean, we have a lot of great activity happening in quantum science in Ireland, and in UCD School of Physics we have the new Center for Quantum Engineering, Science and Technology. So if you're interested, contact us. We'll try, and if you want to drop me an email, or the director Andrew, we'll try and answer some of these questions that maybe Klaus didn't get to. And for sure, we look forward to being able to host similar activities going forward. And I think that ties into a nice one final thing for the people there who are based in Ireland. There is a national conversation going on at the moment about the types of research that your money should go towards. So the funding that we had for organizing today's event comes from the National University of Ireland through a grant that Anthony was awarded. And so the government wants to hear more of the sort of research that you want to see funded. And I hope that Klaus has convinced you that, I mean, quantum technologies really they're a game changer, but there's a lot of work still to do. So if you want to see more of it, I think, engage, let us know what you want to see us doing, and just get in touch. So I think with that, I'm just going to thank Klaus again for the absolutely wonderful talk and for giving us his time. And I pass back to Anthony just to wrap things up.
Okay, great. Well, yeah, Klaus has definitely convinced me in a way, so I'm a believer. Yeah, no, so really, again, thanks so much.